n is greater than or equal to 1. Fibonacci sequence. Fibonacci sequence and Fibonacci recurrence relation. And Fibonacci recurrence relation. Fibonacci RR means recurrence relation. Here, so a sequence Fn n equal to 0 to infinity, in which the first two terms are, which is the first two terms are equal to 1, equal to 1, and starting from third term, every term is sum of two terms of immediate preceding terms is called a Fibonacci sequence. Here, example, f naught equal to 1 and f1 equal to 1. f1 equal to 1. f2 equal to f0 plus f1, f0 plus f1, that equal to 1 plus 1, 1 plus 1, 2. Similarly, f3 equal to f3 equal to f2 plus f1, 2 plus f1, that equal to 2 plus 1, that equal to 3. f4 equal to f4 equal to f3 plus f3 plus f2, f3 plus f2, f3 plus f2, that equal to 3 plus 3 plus 2, that equal to 5. So Fn are called, there are called, are called, are called, are called, are called Fibonacci sequence, are called Fibonacci relation, are called Fibonacci numbers. Fibonacci numbers. Fibonacci numbers are called Fibonacci numbers. The relation Fn equal to the relation the relation the relation Fn equal to the relation Fn equal to Fn minus 1 plus Fn minus 2, Fn minus 1 plus Fn minus 2, Fn minus 2, n minus 2, for all n is greater than or equal to 2, with the f not equal to with 1, that equal to f1, is called a Fibonacci recurrence relation. Is called Fibonacci recurrence relation. Fibonacci recurrence relation. Relation. Fibonacci recurrence relation. Fibonacci recurrence relation. So classification of recurrence relations. Classification of recurrence relations. Classification. Of RR means recurrence relation. A recurrence relation of the form. A recurrence relation of the form. Recurrence relation of the form. C naught here. By AN. A. The C1. C1 can. AN minus 1. AN minus 1. N minus 1. Plus C2. C2N. AN minus 2. AN minus 2. Plus so on. So on. CK. CKN. CKN. AN minus K. N minus K equal to F of 1. N minus K equal to F of 1. Okay? F of N. For all N is greater than or equal to K. For all N is greater than or equal to K. Okay. Oh, N is greater than or equal to K. It's called the linear recurrence relation. It's called linear recurrence relation. Recurrence relation. Linear recurrence relation of order K. Order K. Order K. Of order K. The solutions of recurrence relation. Sorry. Example. Example. AN minus 3AN minus 1. 3AN minus 3AN minus 1. Plus 2AN minus 2. N minus 2. That equal to 0. That equal to 0. For all N is greater than or equal to 1. n is greater than or equal. Is a homogeneous linear recurrent. Is a homogeneous homogeneous linear reconciliation. Linear reconciliation. Reconciliation. With constant coefficient of order 2. Constant coefficient of order 2. Constant coefficient of order 2. Order 2. Homogeneous linear regression with constant coefficient of order 2. Solutions of reconciliation. Solutions of reference relation are a sequence of non-negative in terms uh, n equal to 0 to infinity, which satisfies the given recurrence relation is called as a is called as a solution of the given recurrence relation. There are different methods. There are different methods of solving recurrence relation with substitution method, iteration method, or backtracking method. Second one, method of characteristic roots. Method of characteristic roots. Fourth one, method of undetermined coefficient. Fourth one, method of using generating functions. So, substitution method. First one is substitution method. Substitution method. Substitution method. Substitution method. In this method, the recurrence relation for an is used repeatedly for a general expression for an in terms of n for solving a linear homogeneous recurrence relation of order u of order. You need uh, one one iterative condition, one interior condition. Similarly, to solve a linear homogeneous recurrence relation of degree k, we need to k condition. This method is very simple. Solve the recurrence relation. Example. Solve the RR means recurrence relation. Recurrence relation. an that equal to an minus 1 plus an minus 1 plus n. So a1 equal to 1 by iterative method. By iterative method. Iterative method. Iterative method. Solution. 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 The given recurrence relation is given recurrence relation is an minus 1, an minus 1 plus n and a1 equal to 1 for all n is greater than or equal to 1. By repeatedly applying, by repeatedly applying repeatedly applying repeatedly applying repeatedly applying an we get an we get n we get an equal to an minus 1 plus n that equal an plus 2 an minus 2 plus n plus n minus 1 that equal an minus 3 plus n plus n minus 1 plus n minus 2 right. So on an minus an minus of n minus 1 minus of n minus 1 plus n plus n minus 1 minus 1 plus so on plus 2 that equal a1 equal to a1 plus 2 plus 3 plus 3 plus so on plus n minus 1 plus n minus 1 plus n minus 1 plus n minus 1 plus n. So a1 equal to given no 1 plus 2 plus 3 plus so on plus n plus n plus n plus n plus n. This can be written as from mathematical sigma n equal to n into n plus 1 whole divided by n minus 1 is the before term of this. So 1 by 2 is the relation of the is the solution of the recurrence relation. The solution of the recurrence relation. the solution of recurrence relation. With the solution of recurrence relation. Next. Method of characteristic roots. Method of characteristic. Method of characteristic roots. Characteristic roots. Method of characteristic roots. Let the given homogeneous linear recurrence relation of order k with constant coefficients be of the form an plus c1 an minus 1 plus c2 an minus 2 plus so on plus ck an minus k equal to 0 for all n is greater than or equal to k. Ck is not equal to 0, that is what one. Let t be any variable, then the polynomial c of t equal to t power k plus c1 to the power of k minus 1 plus c1 to the power of k minus 2 plus so on plus ck. Ck is called characteristic polynomial of c of t equal to 0 is called characteristic equation of 1. Solving this characteristic equation, we get the values of t known as characteristic roots. Depending upon the nature of these characteristic roots, we can write the general solution of the given recurrence relation. This general solution will contain k, a number of arbitrary constants. If k is a number of conditions, so uh, given along with the given recurrence relation, we can find the values of arbitrary constants. This method of solving given recurrence relation is called method of characteristic roots. Then working group will see. Example 1. Take example 1. Solve the recurrence relation. Solve the recurrence relation. RR means recurrence relation. an minus 7 an minus 1 an minus 7 an minus 1 an minus 1 plus 2 an plus 12 an minus 2 equal to 0. So for all oh, for all n is greater than or equal to n is greater than or equal to with a not equal to 0, a not equal to 0, a1 equal to 5, a1 equal to 5. solution. Solution. The given recurrence relation is the given recurrence relation is given recurrence relation is an minus 7 an minus 1 an minus 1 plus 12 an minus 2 equal to 0. Equal to 0. The characteristic equation is the characteristic equation. Characteristic e square minus 70 plus 12 equal to 0. Equal to 0. Q minus 3. Q minus 3, comma. Q minus 4. Q minus 4 equal to 0. P equal to 3, comma. That implies E equal to 3, comma 4. 3, comma. That alpha let alpha 1 equal to 3. Alpha 2 equal to 4. Alpha 2 equal to 4. 4. Alpha 3 equal to 3. Alpha 2 equal to 4. The general equation is general equation. The general equation. The general equation is an C1 alpha 1 whole power n plus C2 alpha 2 whole power n. Here C1, C2 are arbitrary constants. C1, comma, C2 are arbitrary constants. Arbitrary constants. Arbitrary constants. So an equal to C1, an equal to C1. Alpha 1 is 3 now. 3 power n plus C2. Now alpha 2 is 4 power n. 4 power n. So equation number 1. Consider equation number 1. Here A naught equal to 2. Here A naught equal to 2. And A1 equal to 5. Correct? Given in the question. Given in the A1 equal to 5 given. That implies C1 plus C2. C1 plus C2 equal to 4. 2. And 3C1 plus 4C2 equal to 5. So solving this, substituting these two, I will get C1 equal to 3, C2 equal to 5. Their printing mistakes, the mistake is there in the equation. Solving these two equations and solving these equations, and solving these equations, we obtain C1 equal to 3, C2 equal to 1. So substituting in 1, substituting these values in 1, substituting routine Ti to UTI, substituting these values in 1. And equation number 1. Substituting these values in 1. We obtain an equal to 3 into 3 power n. So plus minus 1 into 4 power n. There is 1. So C2 equal to minus 1. What C2 equal to minus 1. That equal to 2 to the power of n plus 1. 1 plus 1 minus 4 to the power of n. 4 to the power of n. This is the solution of given recurrence relation. This is the solution of given recurrence and given RR. RR means not really called the recurrence relation. Difference relation. Difference relation. Next. So 6.3.9, 6.3.10. Important, but a long answer type question. 10, 6.3.11, 7 are good as no mark. General solution of given Fibonacci the relation. Method of using generating functions. So discuss one more. That is example. That is 6.3.20. Example. Solve an minus 7an minus 1 and minus plus 10 and an minus 1 an minus 2 that equal to 0 for all n is greater than or equal to 2 with a not equal to 10 with a not equal to 10 and a1 equal to c1 and a1 equal to c1 equals solution. Solution. Oh, solution. Let ax equal to solution. So given recurrence relation, given recurrence relation, given recurrence relation, an minus 7, an minus 1 plus 10 an minus 2 equal to 0 for all n is greater than or equal to 2. Equation number 1. Okay, let ax equal to ax sigma n equal to 0 to infinity anxn nxn. We are given generating function. We given generating function. Generating. Multiply each term with the x power n. Multiply each term each term with the x power n. X power n. X power n. And taking the summation from taking I'm taking the summation, summation. Taking the summation from n equal to 1 to infinity, n equal to 1 to infinity, 1 to infinity. We get, we get we get sigma n equal to 2 to infinity, sigma n equal to 2 to infinity, 2 to infinity, 2 to infinity, minus 7, minus 7, 7x, ax, ax minus a naught plus 10x square, 10x square into ax, a of x equal to 0 to 0 equal to 0. So ax equal to on simplification we have 10. Ax equal to a naught equal to given 10, a1 equal to c1. A1 equal to some value c1 c2. A naught 10. 1 minus 2x. A1 equal to 1, A2 equal to 10. A naught equal to 10 and A1 equal to 6. So 10 plus 6, A of x equal to C1, C2 are arbitrary constant so say R x sub C. So 2 to the power of n, 5 to the power of n. So on continues. Obtain the values an equal to an equal to 3 into 2 to the power of n plus 7 into plus 7 into 5 to the power of n, 5 to the power of n is the required solution, is the required solution, required solution, requires. Okay, this is long answer type question, most important for 10 marks. Oh, okay, okay, students. Today we completed 60th unit. We'll discuss next class 7th unit. Okay, thank you very much. Thank you very much. I'm leaving. Thank you.